This is an introduction to vectors for our next topic. So if we look at this first part here, we're talking about what is a vector. So it says an arrow with the same length and direction is regarded as equivalent. These arrows are directed line segments. Now directed means that the segment actually has a way that it's going, so it's pointing in a particular direction. And the sets of equivalent segments are called vectors. Now a vector has two things. It always has to have a magnitude, which is a length, and a direction. So you can see if we look at one of these arrows here, for example the one between A and B, that has a particular length. So we could call that maybe 3 or something. I don't know how big that is, but that has a length for how long that is, and it also is pointing in a particular direction. So it has the two things that you need for it to be a vector. Now this particular vector here, if I just cut that from where it is, we've got A and a B. There's a couple of ways that we can write vectors or use notation for vectors. We can call this vector something, so we might like to call it maybe the vector A. So you'd call it A with a little what's called a tilde underneath. Now in textbooks they'll use bold here, but because when you're writing by hand it's very hard to do a letter in bold, we just use the little line underneath to tell us it's a vector. We can also use this notation saying that we have a vector going from the point A to the point B. It would look like that, AB. The arrow on top tells us which way we're going. So we're going from A to B. Okay, that's not the same as that because B to A would be going back the other way. Okay, so you have to be very careful about where you start on the vector and where you end. Now there's two parts to a vector. The actual vector has what's called a tail and a head. The tail is what's left at the end, like if a dog walks past you, it leaves its tail at the end. Well, the tail is where you've left what you've left behind from your vector. The head is the arrowhead, or the point on that vector. And when we're talking about adding and subtracting, which we will in a second, we always add head to tail. Okay. Now in this particular example here, this diagram, you can see you've got a range of different vectors. You've got the vector A to B, you've got the vector C to D. Now all of the vectors in this picture are actually the same length. And the odd thing with vectors that can be a bit strange when we get started is that if they have the same length and you can see they're all pointing in the same direction, these vectors are actually equal to each other. And in fact that's equal to OP, which is equal to that vector E to F down here. Same length, same direction. And also G to H. They all have the same length or the same magnitude, and they also have the same direction. So with vectors, we're actually not so much concerned with where they are on the plane as we are with their magnitude and with their direction. Their actual placement on the plane is not really that important anymore with vectors, which is really a bit interesting when we get into things with proofs. So looking at vectors, we can write vectors a couple of ways. Now, the more common way is, we're going to talk a little bit later on about unit vectors, so I'll introduce it here just so that you've seen it. We talk about unit vectors I and j being in the x and the y directions, and we say that a unit vector has a length or a magnitude of 1. So a unit vector is a little vector that has a particular length 1 going in a particular direction. Now we have two little unit vectors that we work with, the unit vectors I and the unit vectors j, and we can make up all other vectors by using the I and the j, and you'll see this later on. I don't want to go into it too much until we get to it, but you can build up, it's pretty much just like building things up with x and y. So for example, maybe this one O to P, maybe O to P is 3i plus 3j, let's say. I'm just estimating from the picture, or maybe 2j. And all we've done is we've just really made up, I'm just saying that this is 3 across and 2 up, just estimating. I'm using that notation with i's and j's, so we will see this in the next couple of sections time. In this part here, we can also see that we talk about, and this notation here is using I and j, using unit vectors. We can also use column vectors. Okay, so we've got a vector here from A to B, which you can see forms a kind of triangle. It's 3 units across and 2 units up. And the way that we can discuss that vector or describe that vector is to use columns. Now the column vectors work by having the x and then the y. Okay, so the direction or the amount of distance in x and the amount of distance in y go in here. So A to B would be 3 across and it would be 2 up. If you had a vector, say for example, something like this, we had CD like this, oops, going down, and let's say it was 2 units across, 1 unit that way, you can see that for CD, the column vector that represents this, you're going across 2, so it's positive, but you're going down 1. You're going in the negative direction for y. So that would be a negative 1. So you can have positive and negative values. You can also have zeros as well. So if you were to have a vector that, for example, just went exactly down that way, maybe for 3, then this particular vector here would be 0, 3. It doesn't go across anyway, but it just goes down, and it would be negative 3. It goes down 3. So you can have zeros in your column vector as well. So that's another way of representing vectors. So 2 ways, the I and J, and we'll talk more about that later on, and the column vectors, which we'll talk about with the next example here. So magnitudes of vectors. If you remember that picture we just saw, we had an A and a B, and 3 units across, 2 units up. So 3 and 2. Now you would be able to figure out at this point how to get the magnitude or the length of this vector, and that would be by using Pythagoras. So the magnitude or length for a vector, we know that this vector is A to B. Okay, for magnitude we use the modulus signs around that vector, and we would say here it would be the square root of one side squared plus the other side squared. So it would be the square root of 9 plus 4, which would be the square root of 13. Okay. The other way that you can look more broadly at what the magnitude is just your basic Pythagoras. So if you've got x and a y, so you're going in the x direction and the y direction, then the magnitude of a particular vector is given by the square root of x squared plus y squared. That's in 2 dimensions, x and y. We can also deal in 3 dimensions, but we'll wait until we get into 3 dimensions for vectors. It pretty much just goes on from Pythagoras, just adding another square for that third direction. In terms of addition of vectors, you can see there's a couple of diagrams here. The first one shows you what's happening when you're going from the point A to the point C. And let's just look at breaking it down. So if we want to go directly from A to C, we don't know anything, we don't know enough information to write down what that is, unless we look at going by a different route. Now when you're adding vectors or subtracting vectors, you always have to make sure that you do this by adding them or subtracting them head to tail. Now what that means is the head part is the part that would have an arrow head on it. So that's the head, and this is the tail at the end. So if we've got 2 vectors here, we actually have the vector A to B, which is represented by U, and we have the vector B to C, which is represented by V. If we wanted to go from A to C, rather than going directly, we can go sort of the roundabout way by going to B first and then to C. Okay, it doesn't actually matter that we went to a different place here. At the end of the day, a vector is defined by where it starts and where it ends. So it doesn't matter what we did in the middle. So it's kind of like going from, Geelong to Melbourne. We could go straight from Geelong to Melbourne and meet our friend at Melbourne, or we could go maybe to Werribee first and then we could go to Melbourne. Whether or not we went to Werribee first doesn't make any difference to the person you meet in Melbourne, as long as you get there at the time that you said you would. So it makes no difference in terms of how to get there, it just matters where you start and where you end and what that distance was there, that length. So when we look at making the vector A to C, we can build that out of the U and the V that we know already. So we can travel along from U, along U because it's in the right direction. Okay, so we've got A and going to C, we go along U, and then because V actually is already oriented correctly so that we have a head with a tail, the head and the tail and the head there, we can go then directly plus along V. Okay, so that's how we can get from A to C. Now this example here shows the same thing. This is the path that we took up here, U and V. Now if we actually wanted to, you can see that U is this vector in space. It's also, I could draw that vector over here, same direction, same length, and here. Same direction, same length. Now v is a vector going this direction. So again, you could draw that anywhere you wanted to, as long as it had the same distance and the same direction. And so we're going to draw it here. Same distance, same direction. Now, in this example, we went along u and then to v. Well, here we've put v here first. So you can see we're going to travel this way. That means we're going to be travelling along that vector v. We're going to be travelling up along that vector u. So it will be v plus u. So what this is showing you is that it doesn't matter in terms of vectors whether you add u plus v or v plus u. The order with adding doesn't matter with vectors, because you'll still get to the same place. You'll have travelled from A and you'll have travelled from C, and you can see it represented here with a rectangle. You can also add using columns. Okay, so if you have a particular vector u and v, say here, so this vector here u would be the column 4, 1, because you've gone across 4 and then you've gone up 1. And then this vector v here would be going across 1, okay, and then, excuse me, I should draw that the other way, because you're going that way, and you'd be going up 3. So this vector here would be -1, okay, because you're going that way, and it's a good idea to draw yourself some axes as well, so you can see that, there's x, there's y. Okay, so thinking about your axes sort of sitting here, you've gone that way 1, so this is a -1 plus 3. So you've got -1 plus 3. If you're adding vectors, what you can do is add across. So you add your x's together and you add your y's together. So 4 minus 1 is 3, 1 plus 3 is 4. And you can see here, if you think about what's going on, if you're going 4 across, okay, and at the end of the day we're going to end up going 3, well, that's because we had to go 1 back again. We went 4 across and then we went a little bit back. So it was like we did that. So we ended up at that 3 here. Okay, so that's where the 3 comes from. And then same with the distance going up. If we started here, we went up 1, and then we also went up another 3. So we added them together to get that distance of 4. So that's why we've got u plus v, which is this one here. This is u plus v. This vector is equal to 3, 4. 3 across and 4 up. Scalar multiplication is another thing that we want to look at with vectors. Now if you have a particular vector, let's say, I'll do this in blue, we had the vector, we'll call it A. If we have 2 times A, that's a vector that is exactly twice as big, still going in the same direction. If we had a vector half A, that's a vector that's exactly the same direction, but it's cut in half. So it would be a vector that's only half as big as the original. When we say scalar, this is talking about a number. You're multiplying by a number. We will talk about multiplying by vectors as well. If we had A again, we can do -1 times A, negative A. It's a vector that's exactly the same length as the original vector, but it's going back the other way. It turns around. And again, you could have things like -2a as well. That would be a vector that's twice as long and also going in the opposite direction. So that's what happens when you have scalar multiplication. Fractions are going to make your vector smaller, and whole numbers bigger than 1 are going to make your vector bigger. We've also got to finish off 2 other things you need to know about for vectors. There is something called the zero vector. Now the zero vector by hand is written as this. It has a 0 in the x direction and a 0 in the y direction, so it can also be written as a column vector, 0, 0. It has no length, so it has 0 length, and it also has no direction. Now there is a big difference between 0 and just 0. They do not equal each other. This is not a vector, this is a scalar. Okay, so there's a difference between a scalar, which is a number, and a vector, which is something with a direction and a length. I mean, the argument would be this has no direction and hence isn't a vector, but it is still defined as a vector, particular vector, the zero vector. So if you get, for example, or if you're working with 2 vectors, let's say you're working with u and v, so let's say u equals 3, 2, and v was also 3, 2. You can see they're equal to each other. So if you had u take away v, you'd have the 0 vector as your answer. Okay, and that's really to show that you were working with vectors and your answer is a vector. Subtraction of vectors to finish off. If you had a vector u and a vector v, and you were trying to find u take away v, what you would do is construct from a u and then look at your v. This would be take away v, like that. Now if we think about how we need to add and subtract vectors, we always need to add and subtract using head to tail. So if we have a look here, we'd have to have u take away v, we'd have to have u, and to take away v, head to tail, it would look like that. So the actual vector for u take v, and that's u and that's take v, would look like that. It'd be a vector going back that way, and you can see it in the picture here more clearly as well. So when you're constructing subtraction of vectors, really think about which one you're subtracting. It's going to change the direction of that vector, and then also how you add, effectively add those vectors together to get the negative in there, so u minus v.